Again with line integrals. I can't wait too much because otherwise later on you will say, okay, it's too late. So the ordinary integral is defined. So I will call this ordinary integral, which is a definite integral, is defined for real valued function on intervals. Now, the difference is, okay, here we replace interval by a curve in n-dimensional space. We call this n space. Okay. So general way to think about integrals is over a curve. When you have multiple dimensions, you have dealing with a space. A curve is the natural thing you should be thinking of. Okay. Described by, so when you
n space.
N space, yeah.
N dimensional.
Yeah, that's in short n space. You can say this is n dimensional space. Like in short n space and dimensional. In an n dimensional space. Right. Okay, by a vector valued function alpha and the integrand. So the thing you are integrating over is a curve rather than an interval. So for ordinary integrals, you are integrating over an interval. Now you are integrating over a curve. A curve is described by vector valued function, right? And the integrand is a vector field. It will denote by BF. Okay. Say this, bounded on this curve. Okay. Now this is called, so this is, as you can say, this is called, later we will meet a more rigorous definition of what a line integral is, but this is heuristically you can think of. This is a line integral. Line or curvilinear or contour, they're all the same. That's why we have a discussion with Sir, the line and curve and contour, everything is same when I talk about integrals. Okay? It's like a curve. A line is a curve. Line is a curve. By definition.
Yes. This straight curve.
Question.
Is a vector valued function alpha vector?
Yes. Yeah, that's what you're going to use. Yeah, throughout. So alpha is our, whenever we say a curve, it is described by some alpha. First, will be some function of t here. You can have a t here, a parameter which is mapping from the interval to the curve. Okay. A contour integral denoted by this. So by a curve, when I said curve, I could have a symbol for curve. I would call it C. So replace that by a curve C. Okay, in an n-dimensional space by a vector field, which is alpha, vector valued function alpha t. Actually, here described by should be a described by now. There are too many bys. So the curve is described by the vector valued function. Okay. replacing the interval by that. So this C comes here in the symbol, and then this. This is our symbol for line integrals. And the curve is called, the curve C here is called a path of integration. Okay. Now definition: continuous, smooth, and piecewise smooth functions. So this is a heuristic. As we said, we didn't demand anything on any properties of the curve. Now we will demand something. So what are those properties? So let J be an interval, be a finite closed interval in R1, a function alpha mapping the interval to Rn is continuous. So when I say function, it really means it's a vector field here. It's continuous on J and is called, yeah, sure it is. It's called continuous path in n-dimensional space. Okay. So that's the idea of a continuous path. Okay, you can think of that's a definition of continuous path. That's continuous. Okay, the function of the vector valued function. So you can say a function, or you can just add a vector valued function here. But from the function, looking at the mapping, you can say what it is. So the path is called smooth. Next, the smooth functions. You can also replace this word functions by paths. So the path is called smooth if the derivative alpha prime of some parameter exists and is continuous in the open interval of V. Okay. So that's your smooth path or smooth function, interchangeable. In this case, then we also need something which is piecewise. The path, yeah.
Is T the argument for alpha prime vector?
T. T is an argument, yeah. So it's a derivative with respect to T. Because alpha is defined, if you look at the definition, it's defined, the interval is J. So T is a parameter, okay. So if you like here, for any T element of J. The path is called piecewise smooth if the interval A to B can be partitioned into a finite number of subintervals, okay, in each of which the path is smooth. Okay. So what do we mean by all of this is that if we have a picture, so you can see the piecewise smooth is the most general thing, because we have smooth paths which are by definition they are obviously continuous and they are piecewise, so there are points of discontinuity. Suppose this kind of paths something like that. So here these are the points.
So step function would be a discontinuous function.
Yeah, that's a discontinuous function. But we're not talking about discontinuous function, we're talking about piecewise smooth functions.
Yes, piecewise. Just a little side note, which I think you will find interesting, is that Fourier analysis was discovered because Fourier wanted to solve the heat equation
Right.
for two objects which are at different temperatures. And when they come together, how does the temperature evolve? Right? So now if at t equals to 0, it's a step function because the temperature of one object is say 1, another object is say 2, or the scale doesn't, exact value doesn't matter. And then what Fourier had understood is that the heat equation has a solution, which is a sine curve or a cosine curve. So he wanted to solve that problem, and so he found out a way to represent the step function, as a Fourier series. And of course, there's a little catch there because there's this thing called Gibbs phenomenon.
Overshoot.
There's an overshoot. So yeah, these piecewise continuous functions are actually very, very important.
ও আচ্ছা হ্যাঁ আচ্ছা আমি তো এখন একটু ব্যস্ত আছি আপনাকে আমি পরে ফোন দিই একটু Okay, thank you. Okay, so these are the points. So these points, this arrow marked points, okay, subdivide the curve into arcs along each of which the tangent. So what is an alpha prime? It's a tangent line, right? So alpha prime that we met here, this is actually a tangent to the curve. So the tangent line, or tangent line, yes, tangent line turns continuously. Okay, so if it's a smooth, you expect the tangent line to turn smoothly, continuously. Smoothly means actually shouldn't use smoothly, continuously here. In mathematics, if you see something moves smoothly, it's very confusing. You have to say, okay, it's continuously, it's one thing, smooth is another thing. Okay, that's one thing. But these are piecewise, okay, because there are finite number of points. So there should be finite number of points of, you can say, discontinuity. Okay.
That point, the tangent line doesn't
Yeah.
transit point,
মানে
right?
yeah, yeah.
Sudden shift of the tangent line.
মানে at this point you don't have the derivative because there is this.
Okay. This point do not have the derivative, the arrow.
Yeah, at this point, if you have a sharp edge, you do not have it.
So we have to apply piecewise integral
Yes.
for this function.
Yeah. Okay, so now the next definition with these pictorial ideas. Now we are going to define the line integral carefully, mathematically. So definition of a line integral. So let alpha be a piecewise smooth path in n-dimensional, so in short, I in dim for short dimension, n-dimensional space defined on n. So my on became a Bengali letter on an interval AB, so it's a on a closed interval. Piecewise smooth paths. Okay. So we can attach a T always if you like, and so attaching a T actually makes it different from any other vector fields. It's a vector valued function because T is just some interval defined over R1. Let F be a vector field defined, and so what do I mean by defined? So defined, I should say defined by this map, which is Rn to Rn, okay, and bounded on the graph of alpha t. Okay. The line integral of f along alpha t is denoted by this. This. Okay. And is defined by so how do you calculate it? So calculation recipe is you go to the interval and you use the tangent vectors to do that, or tangent lines. So it's defined on a piecewise smooth path, okay, so that you can chop it off. We'll see how it works. So what do we mean by chop it off? So let us move on.
Yeah, one question.
Yeah.
Does the function always have to be defined for a similar number of spaces? Like
In this case, yes. Yes. In this case, yes. The definition is yes. Because there's a dot product there. Whenever the integral on the right side, if the dot product won't make any sense if you don't take it from the same space. Whenever the integral on the right side exists whenever. So this statement is not yet done. So we are defined by this: whenever the integral on the right side exists, either as a proper or an improper integral. So error function or Gaussian integral is an example of an improper integral. So let us see something like f. If we write its components, these are the components of f, and alpha has components like alpha 1 to alpha n. So if I call it equation 1, then with, so let's call this with the components, with the components. Equation 1 can be written and becomes as this. Okay. Where the left side can be thought of this way. Let us look at an example.
Sir,
Yeah.
can I explain the equation 1?
So d alpha is vector field. So you're measuring the change in alpha. Okay. But vector field is defined. So this is on the curve. Alphas are on the curve. Okay. Every point on the curve. So this is a curve, and every point is defined by alpha. Okay. This curve is defined by alpha. Okay.
This curve is alpha.
Yeah. This curve is alpha t. Yeah.
T is just a parameter on the curve.
Okay. So you're mapping this.
You can think of it as suppose a particle traveling in a dimensional space. T is the time, and alpha is the position. Just a physical picture.
So A and B here are in the interval, and A vector, B vector are not the same A. They are the different A's on the space.
So what is F?
F is the vector field that you're integrating over on this path.
And so if you think of a physical example, suppose this particle is moving in space, and this particle say is a charged particle or something, and there's some electric field or something, and it's getting some force, and that force could be another vector, and that is
Yeah, so obviously, yeah, you can do that. So there is some force, suppose. Yeah, so for a particle you can think of, but that's for a particle.
So I mean, I'm
You
just
can-
giving you a physical picture.
You
of
can,
that stuff.
you have to do it for anything, on any vector
Integral
field.
of that direction, right? Integral of the alpha.
Yeah, so this is some
that direction.
arbitrary vector field, yeah, along the path. So there is some arbitrary vector field along the path, and you integrate it over the path.
So if you discretize the path into small pieces, and then you can write that as a Riemann sum, the integral, and then if you take the length of the pieces to go to 0, right? So yeah, I don't want to teach it, but I just want
No, that's fine.
to
No.
give different pictures.
Yeah, no, that's fine.
Then that Riemann sum will become the integral, right?
So how it is equal to the left side?
Which one?
I understood. Okay, I understood. The right
This is what I'm writing in terms of this.
Okay. Okay.
You're using the chain rule, right?
Right.
Okay.
It's important that we get this. This is
Yeah, that's very important. Because d alpha is a function of t.
alpha is a function of, yeah.
So alpha is a function. So d alpha is equals to d alpha by dt times dt, which is the change.
Exactly.
So what is the C here?
C is the curve.
Oh, C is the curve.
Yeah. So here you don't see the C because I'm integrating now over the interval. It's very hard today, the rain and everything. I was just thinking that if
They're very committed learners.
yeah, extremely complicated.
So,
No, we are just defining things, and we just define the path over which we will integrate, and the line integral is f vector dot d alpha, and we're writing it in terms of. So left side is the definition, but the left side is the what line integral is over there over the curve, but we have to find an expression by which we can compute things. So you can think right side as the way to compute it. Or also what it really means, alpha, what really means, going to the nitty-gritty details of alpha.
so we group the d alpha to alpha by
So
d.
that's a generic feature in mathematics. You do something abstract, but whenever you have to compute, you have to go down to the bottom and you have to compute.
But the idea I think here is that
It's all elegance above. Deep down, it's all nasty work of computation.
so yeah, you choose a particular parameterization to compute.
Exactly, exactly.
But the important idea is that the result is independent.
We have
of
to,
that
yes,
parameterization.
we have to prove that. Yeah, we will do that. We have a theorem today.
So therefore,
Yeah.
it's a geometric object you're computing.
It's a dot product, yeah, it's a geometric object, yeah. It's completely geometric, yeah. So there is a big thing about parameterization. There's a big thing about parameterization. So you might ask the question that would it depend on, it looks like it might depend on. When I wrote the last line, it looks like it may depend on the parameterization. Actually alpha, we can have a beta, which is t, still function of t, but could be a different representation of the same curve. Then would there be a problem?
So the parameterization between alpha and beta has to be monotonic.
Yeah, there'll be connection, exactly, they'll be connected. There will be a connection between them so that we can show that they are actually equivalent paths with different representations. So we're coming towards that.
Give some examples.
Yes, so right, so we'll look at some example. One example would be this one. So for x is equal, so let's try to understand this equation. So let's have three-dimensional space. T and then C then. So that's one expression which reverberates with this one. Okay. Now this is very simple. That's why you can do this. It's not even depending on the t. It's just it is independent of t. You can see just x. Now a bit more involved is this one. Say, as I was saying out, that the value of the integral is independent. So this is a slogan, is independent of the parametric representation used to describe the curve. So what is that? So that example 2 is this. So let f to be some vector valued function, some mildly horrible for xy with y positive, could be non-negative. So we can have, so let's not, okay. So we want to compute this vector field over a curve. So the curve has a parameterization, say alpha of t, given by this, for t. Okay, this is one parameterization. Okay. And you can compute, and we compute this integral. Now we take a different parameterization of the curve that's called beta of t, say, which is t of I or t, the x derivative, x component of beta, and 3/2 is the y component for the same t interval. Okay. And you compute again the line integral. But they're describing the same curve. Okay. And what you would find that 2 and 3, they are actually the same.
So you have to show that alpha and beta are the same.
Yeah, they represent the same curve.
Is that obvious?
Yeah. Well, that's not obvious. One has to. You have to. Yeah.
That is a key.
Yeah. So I'm saying that they represent the same curve. Yeah.
Does that t has to be on the same interval?
T is an interval.
It doesn't matter which 0 to 1.
0 to 1. Yeah.
No, it doesn't have to be the same interval.
Yeah.
It's from 0 to 1. Okay. In this case, it's from 0 to 1.
This
This is 0 to 1. Yeah.
Doesn't have to convey.
So yeah, we will. There is a subtle issue about that. So we're going to see that in the theorem.
So for example, if you're doing an integral over a circle, you can parameterize from 0 to pi or 0 to 60.
The example you gave us, let's say that a particle in a motion, we are parameterizing with time. Like, so if I observe the same curve at two observers, then two different observers will have two different times, right?
Okay.
So
And their plots don't have to be linearly connected.
yeah.
As long as their plots are connected by a function which is monotonically increasing or decreasing, you should get the same result.
Exactly.
Yeah. So yeah.
Beta.
Beta. Yeah. They define the same interval.
So is there any bar, beta bar?
But you can heuristically check that they actually give you at the endpoints they give you the same value.
You beta prime, what is prime?
Beta prime.
That's a d beta by dt.
Yeah, alpha
Okay.
prime and beta prime. Yeah.
Oh.
So when you see a prime, there is an argument written, so it's a derivative with respect to the argument.
Yeah.
So 2 and 3 are the same. You can compute it. Okay, it's a homework to compute it and see, because I have given you the F. Everything is given. Okay. So also you can go home and plot these things and see that represent the same curve. So this is it's also. It will be hard for me to say because one of the examples I picked it up. I pinched one of the examples. You can come up with one of yours examples. So maybe I would produce another one. But আমি যখন লিখতেছিলাম আমি এত সময় নষ্ট করতে পারিনি, so আমি ওটা I picked it up. Basic properties. One can come up. That'll be a good thing. One can come up with a much simpler one. No, it's not. It's line integrals. Yeah. Basic properties of line integrals. Now next thing. So. Okay. So it's our subtopic 2 today. So our topic was line integral, and this is a subtopic 1, and now our subtopic 2. It's a bit strange. In mathematics, you will say there's sections, section 1, section 2. Trying to basic properties of line integrals. So this needs proof, but they're very straightforward proofs. Just follows from the definition. So they are also left as an exercise. First property is the linearity. And second is the additivity. So mathematical definitions, it's at times hard to address complicated questions at the first go because they're not even defined at that level. So they can ignore quantum field theory problems because they are not even defined yet, properly defined. Okay, so additivity and linearity. These are the properties, and they can be proved from, so C is C1 plus C2, where you have a, as you said, some piecewise smooth curve. So suppose this is your, there's only one, suppose I restrict it to this, my path of integration, then you have two smooth regions, there is a mild discontinuity there, and you just have to compute piecewisely. So the subadditivity is whenever you want to do that. It doesn't have to be a discontinuity, you can always just chop it up and compute length by length. Third thing is the integral, third property, under the change of parameter. It's fairly intuitive, so here some words need to be written. So let alpha be a continuous path defined on interval AB. Let U be a real valued function and differentiable. So whenever we say differentiable, that means first differentiable. Okay. Defined by this map. So there must be some connection between the intervals. Okay. That is given by the change of parameter. You just can't have arbitrarily chosen parameters. There must be some smooth connection between them so that we can use basically our weapon, chain rule. Okay. Then, so we are set, then beta is another vector valued function is defined. So you could write it better and say, okay, then another vector, phrase in a better way, valued function beta. I'm not going to give a t here. maybe I should also raise the t here. This time we are considering this AB. Well, you could keep or not keep a t here, but beta, or let us keep a t there anyways. There will not be a problem. Okay. Sorry, it will not be a problem. This function beta t can be defined on CD by, so this I'm going to define the explicit formula. Okay, so therefore you could put beta of t, even though well, you could put beta of t here, even though you can see t is defined on AB, but that's what this little bit of, you have to be a bit open when you say the t. It's not on AB, it's defined on CD. However, there is a connection between them. Okay. Technically, no problem, but because we have a U here which gives the connection. So, okay. Beta is defined on alpha is a continuous path having the same graph as alpha. So a similar example we just met. An example gives you the same continuous path. Two paths, alpha and beta, so related. So you can give it a name, you can give it a give it an equation. If it's an important equation in a LaTeX document, you give it an equation name. So let us call this 4, equation number 4. So two paths so related by so related. Yeah, so means equation 4. Okay, are called equivalent. And U, so U function, which is between the intervals, is said to define the change of parameter. So a curve is parameterized, right? Parameterized by alpha of t or beta of t. But U is what is making the change. Now, if U prime is greater than 0, that means derivative of U is greater than 0 on CD, okay, because U is defined in CD, then U is increasing, obviously. Okay. So alpha and beta trace out C in the same direction. So that's like monotonically increasing. They are giving you the same graph. However, if your U prime is less than 0 on CD, which means that U is decreasing, So alpha and beta trace out C in the opposite direction. So the property 3 that we mentioned, that integrals under the change of parameter remains the same, that requires a proof. So let us, so we are set with our stage. We explained everything now, everything needed. So next theorem that we're going to encounter shows that a line integral remains unchanged. Oops. Unchanged under a parameter that preserves orientation. So orientation is important. So theorem 1. Okay. So the theorem 1's name is behavior of a, so it's an American English, line integral under a change of parameter. Okay. So let's state the theorem. So let alpha and beta be equivalent. So we now know what is equivalent means. Piecewise smooth paths, then this is the same as this if, so this is not a coincidence. So example 2 we met, we said that they would give you the same result. That's not a coincidence. Okay. If alpha and beta trace out C in the same direction, and this if alpha and beta trace out C in the opposite direction. Okay, so let's go to the proof. And the proof is a very simple exercise of chain rule. It all boils down to be able to write this thing. So the U is the thing here, special thing here. So let me use this one. This is the important thing here that lets us do this thing. Okay. So we are going to prove it for a smooth path, for a particularly smooth path. Then if you have a piecewise collection of smooth paths, then you can just apply it for every segment. So it suffices to prove the theorem for smooth paths. So I'm not writing all this before preludes because they have been all mentioned before the theorem. So those statements need to be borrowed. So let me just give a little sentence here that borrow the given conditions from the preamble of the theorem or prelude to the theorem. Prelude to the theorem has a good ring to it. So we can write let beta to be equal to alpha t. So we have something like composition of maps. So we can go ahead and apply chain rule. So by chain rule, beta prime means alpha prime times what has happened, u prime of t.
What was the formula?
Prelude to the theorem. But before the theorem, we wrote something like we have a alpha and we have a beta, we have a u. Those things need to be mentioned before I say that beta is expressed that way. You have to mention that alpha is a map defined on AB. Then there is a u which takes you from AB to CD. Then beta is defined on CD. Then you can write this.
We can write AB instead of only C. Would it be,
I'm sorry?
whenever you write the C as a interval or curve,
C is the curve. Yeah.
C is the curve. Can we write it as the AB, the range AB?
With the alpha parameterization, yes. For the beta parameterization, it would be CD.
It will be C.
Yeah,
not
because
AB.
because beta is defined on CD. Okay, let me have a quick sketch to this. So what we said, this U is defined on AB. Okay, so then the curve C will become AB when you plug in the parameterization. When you write alpha prime t dt, then you are integrating over the t and it's going from A to B. Because alpha is defined on A to B, right? In that interval. However, when you go for beta, beta is defined on CD. So here is this line. Another vector variable function beta can be defined on CD. Okay. And is defined such that we have a connection with alpha.
So we can take time translations in this way. Say u equal to t plus 2. U of t by t plus 2.
Well, I'm not going to be going to that discussion right now. Maybe later. If there are any questions regarding this, are you clear? So when you write with respect to beta, then you will have to put C and D instead of AB, okay? Because beta is defined on CD. We had a U, that's why we had a connection with alpha, but we did not. We could have had a different thing. If we are not considering such correlation between alpha and beta, we could have considered something else, right?
My question was, can I write AB instead of the curve C? Because this curve C and range AB is the same.
Yeah, for the alpha parameterization. Because
beta parameterization might be different.
Because
range.
you have to see that you are not writing this. You are writing this, right? The curve is the same, but it could have different parameterization. I was saying, it could have different. Okay, so it depends on what parameterization here that dictates what you put here or here, right? So you have a cosine, and you can convert it to y. In some integrals, you can either do the cos, or you can do it y, right? Okay, so you have an integral like cos theta, sine theta, d theta. So if you put y equal to cos theta, then your sine theta d theta becomes dy. So suppose for cos theta, sine theta, d theta, your interval was having limits like 0 to pi. But when you said u equal to or y equal to cos theta, then it became 1 to minus 1. See how intervals change? That's a good example. But I'm not going to go ahead and write it because okay, but yeah. Okay. Okay, so moving forward.
But the primes are different, right?
Sorry.
But the primes are different. Beta prime.
Right. With respect to the argument, right? Yeah. So that's why it's tricky to put t there. That's what is a good point. Now it's tricky to put t there. Okay, because beta is defined on CD. So you have the same t on both sides, it's going to be confusing. So you have to put some different parameterization or something. So take a different parameter in this case. So yeah. When you take a derivative, that's important. So now you do the computation. So let us compute. Compute in this case, let us express. I'm not really computing. Let us express this. So now you see this is CD. Why? Because beta. So f of beta of t dotted with beta prime. Now I'm going to give a t here, understanding that the same t is going, but let me, shall I, okay, I mean, I'm assuming you are matured. And t is dummy. T is an integration variable, so there is a lesson, it's a dummy variable, it doesn't matter what you call it, as long as you're not confused.
You should do something like a heart or something.
Yeah, could have, but I already defined beta t somewhere else, so I have to go ahead and fix that. I just don't want to do that.
Is this dummy variable?
Yeah, it's a dummy variable. Yeah. So, okay, so the vector. Okay, fine. So now what we're going to do? We're going to plug in the. So if I plug in, then I have to be careful, because if I plug in, okay, for the first level I can put this. For the first level, that's all right, because I'm just writing down beta prime of t in a different way. But the next term I have to be careful. So we just express this with this. Now I want to do this calculation here. So define something called v as u of t. So dv would be u prime of t dt. So this part will be your dv. Okay. And this argument will become v. Okay. And your limits will also change accordingly. Become u of c, it will become u of d. Still have, well, wait a second. Nobody pointed me out. There is a subtle problem here. Not a problem, but subtle, not a problem here actually. But on this line there'd be, is it a problem? I can also change here. It's not a problem, but I can change here as well. আমি তো এখানেও চেঞ্জ করতে পারি, তাই না?
Sorry?
Yes.
Because now everything is with respect to alpha now. I can produce a beta, you can replace the beta by alpha because they represent the same parameterization.
You've done the change of variables. Yes.
Yeah, so could do that.
I mean, if you were to be, yeah, exactly, because that's actually the way to do it, because if you look at the first term, the middle term, then it's f bracket beta t. That is a different function of t than the next term, which is a function of alpha t.
Yeah, it's alpha u of t. I have to give a u of t. Yeah.
Why
It's
u?
Yeah, because beta is defined in a way.
Yeah, but that's you don't need
So this is the composition. So
It's just a
Yeah, it's
composition.
composition. So what I'm trying to say is that you're actually doing a different integration. Currently, you're doing a different functional integration in the second case, in the first case, which will depend on the explicit. So the function, the integrand, is different in both cases. In these two cases, although you're getting the same result in the end, and therefore, what I'm saying is that f as a function of beta of t is a different function than f as a function of alpha of t. Right?
Yeah.
You agree?
Yeah. So yeah, they do look different, and they. So, but okay. So my point was, it was a very subtle thing that I'm just changing beta to alpha. It's straightforward, but subtle. Okay, is it okay with everyone? I could do that, right? I haven't done. If I did, have I done anything
So
wrong?
I think that one thing that I think can perhaps envisage doing is that in the example that you gave them as a homework,
Yeah.
you change the form of the curve, right?
I change the curve is the same. I change the
The
parameterization.
parameterization, and you show the parameterization explicitly.
Yeah.
Now, what one has to work out is that one has to show that the vector field also changes. Its representation
Right.
also changes when you change the parameterization.
Yeah.
Right?
Yeah.
So that the integral remains the same.
Yeah. So they will find it out when they plug that in. When they plug it in, then you see that they're different. However, when you compute it, good. Okay. So okay, that's the proof. Why? Because what is V?
Is the dummy variable.
Yeah, this is yeah. Okay. So this is done with a little bit of salt, because I'm gonna write this and forget about the parameterization with respect to t. So why the plus minus here? So the plus minus here, plus means stands for u of c is equal to a and u of d is equal to b. Then it's a plus, that means alpha and beta are tracing out the path in the same direction. But if the u is such that it interchanges them, then there is a minus sign. Okay. So that concludes our proof. So next concept, subtopic 3, is open connected sets. So let S be an open set in Rn. Okay. So S is called connected if every pair of points is actually path connected in this case. If every pair of points A and B in S can be joined by a smooth path whose graph lies in S. So slightly I'm going to mention is path connected. Because connected sets are topological, it's a topological thing. So whenever we cannot write it as a disjoint union of two sets, then it's connected. Whenever by set. But we are not going into the topological definition.
It's more rigorous open path.
This was the paths. Because we are drawing a line between 2 points.
The book mentions theory path.
I'm sorry?
And in the book, Aristotle.
Yeah. He doesn't measure it exactly. Yeah. So topology doesn't require money. Don't need to talk about paths. Paths come later.
Okay, what is it? I'm not following the.
There is something called connected sets that has a definition in topology, which is if you this is
Geometry. Just read it.
this is a path. Yeah, you have the notion of a path, then you can define path connected. So there is a topology sine curve, which is connected but not path connected.
How is it different from the definitions of balls? Like say an open set A can be defined by only balls.
No, in general, when we consider topology, there is no paths and everything because it's a more complex definition. You are considering a set, and when we are considering this, you are if you take step with the topology, there is no notion of distance or anything. You have to follow the axioms of topology. There are 3 axioms. So there is no notion of paths or distance or
No, he's talking about metric topology.
maybe. So,
I think there's a relationship with metric topology.
yeah, because
The set, whatever open set you're looking, you can cover this with some open balls, right?
Yeah.
And from a proof we have done that the balls are continuous because there cannot be a discontinuous.
And a ball continuous doesn't. Ball is a set. A set continuous doesn't make the map between set. You can say it's continuous. Or
No,
not.
I'm just saying that when you have a ball, every element is means. I think I will show you the problem that you gave. I think limit set.
Yeah, but we are cool with this definition. Okay.
Yeah.
So then let's move on. Then. Okay.
So I was thinking that how they two are the same line, right?
Okay, we will look at that. Okay. After this session. So in S, oh my God, why time is running so fast? I don't have any idea.
That means we are having fun.
Really?
Time flows together.
I don't seem like my brain doesn't tell me. And if I'm covering too many materials, I'm very happy. Okay, so good. Okay. So I'm supposed to. Can be joined by a smooth path whose graph lies in S. Okay, where am I? Okay, acha. Okay, then alpha. So please take this with a little bit of salt in your mouth. The two A's are different. I'm sorry?
Scalar and
Yeah, so these A and B's are intervals, and these A and B's are points on the set S, which is in Rn. Okay, for alpha t in us. Now let F be a vector field that is continuous on an open connected set S. Okay. Choose 2 points A and B in S and consider the line integral of F from A to B. Okay. So what would that be? So that would be something this. Now, the thing is that when you look at it, it must come to you that it depends on the path that you're taking. Right? When A, B are 2 points, but I can join them various ways. Okay? So the question is that, or you might claim that in general, and that is also true, that the integral, such integral, depends on this is a definite integral, on the path, and defined in a closed interval, obviously, a to b, on the path, okay, full stop. Which path you take depends on it. But for some vector fields, in the line integral only depends on the endpoints. So this is what we want to understand. What is so special about them? So to answer this question, so who are they? What is the question? Who are they? Okay. So to answer this question, we require fundamental theorem of calculus for line integrals. We require the first and second fundamental mental. Yes, why nobody focused on mental and the fundamental? Fun and mental. Fun.
Yeah, they have a lot of fun. It's all mental.
It's mental. Well, all the fun is mental. So yeah.
ক্যালকাটার লোকরা আমাদের ঠান্ডা আমার যখন কেন্দ্রে গেছি আমার ছিল তখন তার মানে বোঝা ঠান্ডা দিত না এই মানে ঘন্টা ছিলি এই সাংঘাতিক ঠান্ডা দিত ইনসাইট
Oh, acha. Oh, acha. Interesting. Very interesting.
Indians.
হ্যাঁ কলকাতার
For line integrals. So theorem 2. Okay. So let phi be a real function. Oh shit. Phi be a real function, that is, so I'm writing the theorem, yeah, statement of the theorem. Yeah, this is a prelude to the second fundamental theorem. This is not the second fundamental theorem. We need something more before that. Something before that. Okay, so let phi be a real function that is continuous on AB, and the integral phi prime of t dt exists. So theorem assumes that it exists. If it doesn't exist, the theorem is not applicable. If phi prime is continuous So phi was continuous. Okay. Now phi prime is also continuous. If phi prime is also continuous, on the open interval, we have, so the boundaries, you can have some spike. You saw piecewise smooth. You can have something, right? So we just don't want that. Still, our theorem is good. So that's why in the theorem we do not mention it. So this is the wisdom of Kovic, sir. When he was teaching us, he always say, if you have a problem with 1 or 2 points, not a big problem. If you have a problem at 1 point in a potential square well, whatever. If you have a problem at 1 point, that's not a big problem.
So, according to linear theory, what we call, say in quantum mechanics, what we call like a square interval curve, a function, is actually not a function. It's an equivalence class of functions.
Yes.
Where they all differ by a finite number of singular points, isolated singular points. But so according and the Lebesgue measure, it could basically makes them equivalent, right? So yeah, that's basically what we're saying.
Yeah. Exactly. So the proof, let us briefly go through the proof for each. Okay, so for each comes little late. So define f of x a to x phi prime of t dt. Okay, so define this for each x ab. So with this definition, what we want to prove, I forgot what I gave, probably this is equation 5. So we wish to prove, we can restate what we want to prove in terms of f. We want to prove this. F of b will be phi of b minus phi of a. Sounds cool? Okay. Good. Okay, we should prove this thing. Now, to prove this, we need the f to be continuous in the interval AB. Okay, so we will need to prove that. Okay, so for this, we need f to be continuous in AB. So let's prove that. Consider
Would it be f of b minus
some
a
C.
x?
Well, C doesn't have to be there. I'm sorry. Oh, এভাবে লিখতে পারি আমি. F of what is that?
F of b minus f of x.
No. Which this one? Equation 6?
Yeah.
No. You just put in the b and this is what. So you compare with 5, you find the same thing. So consider this. Consider C, which lies in the interval, or could be at the boundary points as well. Okay. Then, I think should say consider. Consider this. Sorry about that. I want to consider this for C between the boundaries. C consider kore ki korbo, right? Since, so am I okay with it? Okay, just keep track of what I'm writing, okay, so that I don't end up writing something uncool. Since phi prime is bounded on AB, okay, there exists an M, okay, such that it's a real number, such that my phi prime of t is bounded. If phi prime is bounded, so I can write it like this. Okay, now I'm going to integrate. Now we integrate the inequality. Integrate the inequality. Okay. From, well, integrate the inequality in the interval or on the interval. Everywhere I said on. So, on C comma D. To obtain, what do I obtain? I'm sorry, it's not going to be C comma D. It's going to be C comma X because I'm considering C to X. X minus C less than. So phi prime T by definition. So if it is equation 7, using this definition, this will be f of x minus f of c. And this will be mx minus c. So here we used equation 7. We didn't use an n with it, no? EQN for equation. Zoidberg used it Q. That's nothing. Anyways, the instruction was you always write EQ. I thought it was very standard. Now we use what? And now take limit. We take x goes to c limit, and by sandwich theorem we get very powerful theorem, sandwich theorem. We can prove a lot of things with this in analysis. Yes. That is, we have proved that f is continuous on this interval. Okay. So by the first fundamental theorem of calculus, okay, not for line integrals, but what is colloquially known a single variable, f is differentiable on an open interval AB with f prime of x equal to phi prime of x for any x in element of AB. So let us refresh ourselves with what is the first and second. So first and second, the difference, okay. So one deals with indefinite integrals first. The second theorem deals with the definite integrals. And okay, so here we're using the first term. So what is that? That is this. If you have a phi of x, so I have to be careful not to mess up with it. So let me use a different letter. Let me call a of x. Should be on the proof with the phi prime children. Phi prime now suppose of x is sum g of t dt of sum a to x, then it says that a prime of x is equal to gt. Gx, I'm sorry, not gt. Gx. And that's the first fundamental theorem of calculus. So your a have to be differentiable on the open interval, and then you can write this. So here our f is doing the same thing. Why? Because look at the definition of f. Okay. So you require that. Okay. So f is continuous, and by first fundamental theorem of calculus, we are saying that this is true. However, yeah, so this is, yeah, so if you have this, then f is differentiable, and then you have this. So we use that to write it down. Now I'm going to give it, okay. Now by the, okay. Now by there's another theorem which is called zero derivative theorem, which really means that if the derivative of something is zero, that means that something is constant in that region, right? So by the zero derivative theorem, that is f prime of x is equal to 0 for each x in AB, okay? That is if then f of x. So here when I'm saying x, this is always in the interval. So is that a point in the interval? Yes, it's a point in the interval. So it's a vector. Okay, f of x is equal to constant, right? Where? On AB. So by continuity, okay, we can write this that f of x. So what is this? So what am I doing here? Okay, so by continuity আসার আগে এটা আমি একটু মেনশন করে দিই যে that is now f of x minus phi of x. I can write it this way, right? Okay, now I am using by continuity to write this. On the closed set, okay, because you know the continuity definition that if we define it, it's continuous on the open and continuous on the closed. We said f is continuous on the closed set, so you can do this. And we also said phi is continuous on the closed set. That's the first definition of the theorem. So we have it, right? But in particular, we could say f of b minus phi of b equal to f of a minus phi of a. You can do that because it's true. However, f of a is 0. Why? From the definition, it was a to x. So f of a is 0 because it's the same point. So let us look at the definition of f of a. A to x. So if x is equal to a, this is 0. Okay. So therefore, the theorem is proved. Okay.
So what was the statement of the theorem? Oh yeah, find the phenomenon.
No,
Find
that,
the minus phi.
yeah, exactly, yeah. So this is the
So
statement.
you quoted a theorem to prove that theorem, right? You quoted a zero derivative theorem.
But these are from ordinary integrals.
Yeah, which is
Also, there is
but that's basically the definition of the antiderivative. Right?
For yeah.
and we also proved that differentiable function is continuous. So the differentiable function is continuous.
Yeah.
We also proved to be strong. Okay. So limit x up to c, f of x equals to f of c. So this is the definition of continuity. But we started with phi as a function differentiable. So when we are considering this, gets down to limit x equals to c, f of x equals to f of c. So that means differentiable function is continuous.
Yeah, so fundamental theory of calculus comes from here. Okay. So whenever you have this, then a is differentiable and a can be written that way.
No, what I'm saying is, মানে আপনি যেটা বলেছেন যে মানে আপনি অলরেডি এখানে আরো একটা জিনিস প্রুভ করেছেন।
Yeah.
যে মানে ডিফারেন্সিয়েবল ফাংশন যে কন্টিনিউয়াস হবে এটা আপনি প্রুভ করেছেন। যে লিমিট x applies to c f of x equals f of c. এবং আপনি এটা স্টার্ট করেছেন phi prime of x is a differentiable function.
I'm sorry. Phi of x, f is differentiable.
Phi is also a differentiable.
Yes, phi is different. It is given in the.
ওইটা থেকে কনক্লুড করেছেন যে হলো লিমিট x applies to c f of x is equals to f of c.
এখানে where
না
here?
এই যে হ্যাঁ এটা হলো f এর কন্টিনিউটি
Right. এখানে আমি কোনো phi ইউজ করি নাই।
না এখানে ফাই ইউজ করবেন বাট
Right.
আপনি ফাই থেকে এখানে এসেছেন।
Yes, আমি phi থেকে এখানে এসেছি। Right, exactly. Phi থেকে আসতে হবে। Yeah, phi থেকে আসতে হবে, right? That's a trick. So define that way so that I can use the. That's why we demanded phi prime is continuous.
মানে আমি এটা বলছি
Yeah.
যে হলো মানে লাইক আমাদের ইয়েটা কি আমরা সবসময় ধরে নিই যে ডিফারেন্সিয়েবল ক্লাসের সবসময় কন্টিনিউয়াস হবে।
Yeah,
So
obviously.
you proved it here.
Yeah,
You proved it here.
yeah.
Can I ask quiz this question? Is x a differentiable function?
F of x equal to x.
If f of x is that a differentiable function? No, f of x is equal to x. That function.
Oh, sorry. That's
Is there a differential function?
Oh, sorry. That's
Yeah,
Yeah,
your function
x
is
is
equal to
This
x.
is a line.
It is a differential function, right? So I get it.
The line.
f of x is equal to x.
Yeah.
Okay.
Or is it an x?
Right. Okay. মানে আমি একটা ইউনিভার্সিটিতে পড়াই সেখানে যারা ইন্টারভিউ করতে আসছিল তারা এই ম্যাথমেটিক্সে তারা বলে পারে না এই কোশ্চেন করতে না তুমি বলছিস না যে
ও আচ্ছা না স্যার ওইটা হলো ইয়ে সাবজেক্ট ছিল যে হলো if I take mod x
oh mod x that's a differential function. Okay. What about mod x? Is that a differential function?
Yeah, জানে।
Huh? No. Right?
no but if I
Piecewise differential.
yeah but is it differentiable at 1?
Yeah, it's differentiable at one.
It is not differentiable at the origin.
Then theorem.
It's only not differentiable at
Oh, right.
for our x to the half. Is it differentiable?
Where?
X
Where? Where? Differentiable. It is a good point. Differentiable where?
Yeah, at what point?
That's x. That's it.
x equal to 0.
Yeah, so
Is it?
you have 1 over square root x.
Yeah.
Is it differentiable?
You have 1 over
square root of x. Is it differentiable at x?
X equals to 0.
It's not because you have a 1 over square root of x.
Because
The limit
I
is
like the limit.
Yeah, that's not x squared. 1 square root of x.
Square root of x.
Square root of x and y square root of y.
I he's asking if it exists or not. You have to.
Okay, it is not differentiable.
You know?
The limit does not convert at x equal to 0.
And
The limit does not convert at x equal to 0.
yes.
Also, negative of x is for negative values of square root of x.
Exactly.
Imagine.
But ও তো জিরোতে বলছে so but এখন কথা হচ্ছে it is differentiable if you exclude 0 with the negative line. Okay. Anyways,
Yeah, I mean, I just like, I just threw those, মানে আমার মনে হয় যে একটু মালপত্র reality check করে ভালো। We are not, I was, sorry for interrupting. I
No,
was
no,
at the interview board yesterday. Rahul, please edit this out. We were hiring statistics teacher who would teach statistics at the fundamental level. And so, ওরা আর পারে, ওরা এই পারে, ওরা সেই পারে. I'm not a statistician. আমি ওদেরকে সবাইকে জিজ্ঞেস করছি যে, can you show why the product rule of probability exists? Independent event will have the product rule, probability cannot product general probability. Only one person was able to answer.
they could use the Venn diagram.
Exactly. Now, Venn diagram, I mean, যেভাবে, and the other question I asked everyone is that, can you tell me write down, what will prove basis theorem? They are statisticians, right?
They didn't write down.
One person who could answer that, she actually proved the first problem using basis theorem. So she's very good. We hired her immediately. I mean, she was a problem. The other person came sort of close to writing down basis theorem, but he could not figure out some of the subtle notation. So what I'm trying to say here is that these people were discussing statistical models are, artificial intelligence, Bayesian learning models that they are going to do research on, PhD on. But they don't understand the basic ideas they don't have the intuition, basic intuition, right? So I think that's why I think that it's good to have frequent reality checks. That we are not just learning these really fancy stuff, but we also know we can apply it intuitively, right? So yeah. So sorry for interrupting.
No, that's fine. Yeah, that's not that's the point. Okay. Now next. Okay, let us wait. Let us have a few more minutes.
Abhijeet, signature move.
So probably this is theorem 3 for the day, and this is the cornerstone theorem for the class. The second what did I do? Fundamental theorem of calculus for the line integral. So let phi be a differentiable scalar field with continuous gradient on an open connected set. So that's why we needed the open connected set, because our theorem requires it. Then for any 2 points A and B joined by a piecewise smooth path alpha. Okay, so you see now we are using alpha as path, not even C, not the curve. We have, so that's the statement of the theorem. Okay. In spirit, it looks like the earlier theorem, no? In spirit.
Sorry?
The earlier theorem.
Yeah. It's a special case of it. You can show it from the first.
In spirit, it's in spirit. So it's a single variable. Now you have a. Okay. Let's prove it. What is this? Proof. Okay, choose any 2 points A and B in S and join them by a piecewise smooth at alpha in S. Okay. Now, or defined on AB. Let alpha is smooth on this closed interval. Okay, tahole these are all given in the theorem. তাহলে আমরা কি দেখতে পাই? দেখতে পাই
The alpha belongs to X.
it's a path in S. When I have points and I'm, yeah. S is in Rn. So alpha is actually an Rn. Okay, very good. So far so good, nothing new. Now our hidden weapon. Not so hidden. Chain rule.
সেগুলোকে আমরা ওই ই করব একটা একটা
We like
one track one trick pony.
one trick penny, exactly. We have one 5 minutes when everybody used to do the same. You know one good thing, you just play it again and again and again. Yeah. So you know only one language and you translate everything into that language. And you just convert it, yeah. Maybe that's not, is that a good way to learn other languages? Maybe or not. I don't know.
They say that if you learn a few languages, then it becomes very easy to learn two languages.
I see.
But it's not true. It's more than that.
Okay.
It depends on the origin of the languages.
Yeah.
It's an aspect.
If they have the same origin, then it does.
Okay. Okay. So by chain rule, okay. So because it is true now, we are going to use our earlier theorem now. So this is okay. So we have an equation. What is this equation? So 6, or I forgot. Because I forgot, these are new equations.
I think it will be sad.
I forgot. Okay. তোমরা আমাকে এক্সকিউজ না করলে আমি চলে যেতাম এখন আমার কয়েকটা সেকেন্ড গেল 20 seconds gone as nebula phi. So I'm going to run. Okay, it's continuous, not constant. It's continuous. Constant লিখতে গেছিলাম কেন? Continuous in S. Okay, this is continuous in S. G prime T. So G, well, so this is continuous, this is continuous, this is continuous. Okay, so eto is continuous on AB. So by theorem 2, our theorem 2 for the class today, what we can write? You can write, so you see you have a GT. When you convert to GT, it's a one parameter, then we can use our theorem. Right? That's what the trick, one pony trick for this case. Okay. Okay, but however, because let me write down the integrand first, then this would make some sense. These are not vectors anymore. Why? Because they are connected by that. So that is G of B minus G of A. But that's the proof, you know. Because what is G? G is okay, and that's the proof. So this is the proof if alpha is smooth. But I think we need to also show, because our statement of the theorem says piecewise smooth if the points have some points were not differentiable. So we have to do a little bit more, So what is the little bit more? So let's chop up AB. So এখানে একটু বলে দেওয়া দরকার এই জায়গায় হচ্ছে for the piecewise scenario, chop it up AB into, say, a finite number of them. By the way, you cannot have infinites, into say a finite R number of intervals, say tk minus 1, tk, okay, for some index set. K belongs to some index set I. Okay, where each in each of these subintervals alpha is smooth. Then we have our integral alpha, and we chop it up. Okay. It's nothing but, so we have proved it. So these are all smooth. Because these are all smooth, okay, so that's the theorem proved. A remark?
Sorry, that's
It will take 1 minute, 1.5 minutes.
no. What I'm saying is that's not the proof, right? Because I mean, you have another step where you have shown that the in between terms are all canceling out. Right?
No, there's no cancellation. We don't need to do the cancellation.
So
But this is just, yeah, this is, yeah, well, you want to say that you want to have cancellations. When I'm saying that you have this, then you have this, then you have this.
yeah, but your theorem statement was that the integral, if you go out a little bit,
Yeah,
well, your left hand side is the limit from A to B,
A to B, right?
and A is the first point and B is the last point.
Right,
Your theorem was that
T1,
the integral
T2,
of
T3.
gradient of phi from A to B was
Yeah.
phi of
So you want to cancel,
E minus phi of A. So,
so you want to cancel these things.
Yeah, exactly. So
Yeah,
what
yeah,
I'm
you
saying
can.
that- so-
That is, we are not doing it. Yeah, that is understood.
No, you can just point it out. That's what I'm saying.
Yeah,
Is that they have the
But
same
we- but-
value, so
yeah,
they all cancel out.
they would cancel.
All the middle point, they occur twice in different signs.
Yeah.
So they cancel out.
মানে একটা integral last point, একটা first point. So that's why but that is understood, I think, because yeah,
Right?
that is understood, I think. Okay, I think there is that not understood? মানে তাহলে
Is
আমার
that understood?
But explicitly saying is
Is that
okay.
It's
আচ্ছা.
pedagogic, it's a better.
Okay, so okay, very good. Acha, so the remark is well, at the end of the day, acha, আমি আসলে লিখি নাই মনে হয় last line, that's why. Okay, last line. If I have written the last line, that would have been.
Yeah, exactly. That's what it is.
Sorry, I forgot. Yeah, I thought I should have. ভাবতেছি কি. Yeah. So as a consequence, I'm running with the time. So yeah.
You're eating dinner already.
Yeah. What? Dinner?
But you're running of dinner already.
As a consequence of the theorem. Thank you, sir. I forgot. I shouldn't have. You were right. I shouldn't have finished it here. Yeah. Even though, yeah. As a consequence of the theorem, we see that the line integral. Okay. What do we see? Do we see actually? What do we see? What have we proved? I'm going to write this actually. This statement you can give. Does it depend on the path? It doesn't. It doesn't depend on the path. There is one thing. This is an exact differential. This is an exact differential. It doesn't depend on the path. Okay? So physics people learn it this way. You have a definition for exact differential. You can write it this way. That's it.
Because everything is smooth that
Everything is smooth and everything is smooth. Everything is smooth.
It's a conservative field.
Character terminology. That is the conservative field.
And that's why you can write as a gradient of a scalar function, which is a potential.
Yeah, but
This alone.
yes, physics is one line done. We are going to take 2 classes. We'll do that, but with proofs.
মানে আমরা যখন ইলেকট্রিক ফিল্ড ইউজ করি ইলেকট্রিক ফিল্ড কে লেখা যায় gradient of phi এর জন্য the integral of electric field over a path is actually
That's the electrostatic electric field.
electrostatic
Electric field.
electrostatic.
And so, as a consequence of the theorem, we see that the line integral, where is this? Where is the line integral of a gradient is independent. So such যেটা বলছে ওটাকে আমরা অ্যাপ্রোচ করতেছি যে ইন্ডিপেন্ডেন্ট সো কোন ধরনের ভেক্টর ফিল্ড হু আর those special vector fields whose line integral does not depend on the path. They are special vector fields who are gradients. Okay, the speciality is in the gradient. Okay. And they have a name, it's called exact. These are called exact stuffs. Okay, this goes to the cohomology. This goes to the heart of cohomology, what Sir was describing. So this is if one wants to know better, it's independent of the path in any open connected set S in which the gradient is, so that's how math people write it. Oh my god, it's continuous. Still, it's a simple statement, but you have to write everything down.
Wouldn't you say that that's a Theorem homology?
Yeah, exactly. Yeah,
Other
yeah.
cohomology
That,
results.
yeah. This is the Theorem column. Yeah. So when you say cohomology, it's a Theorem.
Outside the cities.
Yeah. Yeah. Sorry. We should mention this is a Theorem.
Milan would not be happy. Milan would not be happy with that definition.
Oh yeah. Which one? Exact definition.
That it was a homology. Exactly.
Oh, acha, he will be considering a general cohomological scenario. Okay, I see his point. But he will also see that why I mentioned it, because it is in this discussion it connects with that one. Anyways, okay, I shouldn't have probably. For a closed path, this is obvious, no? Yeah. This is for the closed path. So there, yeah. Yeah. Okay, so that's it for today. Okay, so there is a homework. Not yet done. Homework is please look at the proof of first fundamental theorem from Apostle. For line integrals. That's the homework, because we're not going to prove it, we're going to use it. So if you don't understand, let us know.
First, fundamental theorem
This is a homework
of line integrals.
for line integrals.
Are you going to prove x